Alright, hello. This is Nick Sedano, and I am doing the midterm 1 extra credit for problem number 1, and this is the one I lost the most points on. Alright, let's get started. So in this problem, we have a car with mass 1, which is right here, and it's traveling to the right at a velocity of v1. This collides with the second car of mass m2, and it's traveling at a v2, which is our unknown for the equation, and it's traveling at an angle of theta. And after colliding, the cars stick together and travel off in a perpendicular direction to the initial velocity of car 1. Alright, and so for part A, we're going to find the initial velocity of car 2 before the collision. Let's get started. So, first off, what I like to do, write down the knowns of the equation, just so we know what we can use. So knowns, we have some pretty simple knowns. We have m1, m2, v1, and theta. And we are trying to find, in this first one, we're trying to find v2. And another known thing is that this is an inelastic equation, or inelastic collision, which means our momentum, or p, is conserved. So normally what that would mean is that m1 v1 is equal to m2 v2, or m1 v2 plus m1 v2 is equal to the two together times the final velocity. But in this situation, we can't do that because m2 is going at the angle. We have to decompose that into two different velocity vectors. So again, like I said, m1 is simple, we just have v1. But for m2, we have the v sine of theta for the vertical direction, and we have v cosine of theta for the horizontal direction. So now we're going to have two momentum equations. Let's start off with the horizontal one. So something we know about the horizontal one is the final bit of it is going to be 0, because as we can see, after they collide, everything's going up, there's no horizontal motion. So we can put 0. And then our initial ones to the right, like I said before, we have m1, v1, and then we also have the m2 v cosine of theta, and that's going to the left. So it's going to be negative m2 v cosine of theta. And then for our vertical one, m1 starts out with no vertical motion, so we can just include the v sine. So we have m2 v sine of theta. And then now we can do the adding of the masses times the vf. So these are the equations we're wanting to use. So for A now, what equation of these should we use for this one? Well, the second one is not viable because we have two unknowns. We have the v and the vf. We cannot solve for this. But in this first one, our only unknown, since we have the 0 on this side, is this v. So we can just solve for that. And we know, since these are equal to 0, subtracting it from each other, they're just equal to each other in general. So we have m1 v1 equal to m2 v cosine of theta. Now just to do some rearranging, we divide both sides by m2 and by cosine theta. And this is we get v by itself. We have m1 v1 on top, and then underneath when we have m2 cosine theta. And then that is our v, that is our v2. So now we know the initial velocity of the mass 2 before the collision. Now we want to do after the collision. And now that we have our v2, we know we can solve this equation as vf is the only unknown. So let's rewrite that real quick. We have m2 v sine of theta is going to be equal to m1 plus m2 times the final velocity. And this one is also, we're just going to simplify it by dividing both sides by m1 plus m2 to get this vf by itself. So we're going to have the final velocity is equal to m2 v2. Now that we know it, I'm just going to put a little thing. This is equal to v2. v2 sine of theta, that is over m1 plus m2. And that is our final velocity. And yes, you could also write the v into this, and that would be m2, and then in parentheses, m1 v1 over m2 cosine theta times sine of theta all over m1 plus m2. This is the expanded equation, just in case that's what you guys want, but that b2 is our known, and obviously we could put the m2 cosine theta on the bottom and then cancel out m2. Yeah, that is our final velocity for B. So yeah, that is equation number 1 on exam number 1. Thank you.